And we're back to talk about properties of logarithms in this video, and then use them to solve some logarithmic equations. And then I'll also start doing some calculus. Now that we have logarithms, we can do more calculus of exponential functions than we could before. And hopefully with this video, then you can do completely the first set of homework, sections 4.4 and 4.6. And then the next video, section 4.5, which will be the final video for that week, for this week. It might be a little longer. It'll involve actually derivatives of logarithms. Anyhow, so hopefully if you start working with some of the problems, you'll get the sense that logarithms and exponentials are kind of two sides of the same coin, and that to everything we can do with exponentials, there's like kind of a mirror thing you can do with logarithms. And so the properties of the logarithms kind of mirror the properties of exponentials. And we're not going to prove things in this class, but maybe in the live meetings I'll indicate like how you think of these, how you go about proving these. So here I'll put a property of the ln function, and here's property of exponentials. So if you remember, we talked about this earlier in last week. Also, I think I did this for general exponential base, but you have e to the x times e to the y is e to the x plus y. So if you multiply two exponentials, you add their exponents. So the version of this in the log world is the logarithm of a product. The logarithm of a times b is the logarithm of a plus the logarithm of b. Right? And so you could kind of imagine, right, the logarithm of x times e to the y. So if a is, e to the x and b is e to the y, well, this would be the logarithm of e to the x plus y. And then by what we discussed in our last video, right, this is x plus y, but that's exactly the logarithm of a plus the logarithm of b. Right, so that's exactly the logarithm of e to the x plus the logarithm of e to the y, which is the logarithm of a plus the logarithm of b. So that's how you prove it in that case. So I did a little proof there. I'm doing this because I think you can memorize these properties, but I think if you have some idea of why they're true, then it's easier not to get confused about them. But that's my view. If you don't like that, if you like to just memorize them, by all means, I'm happy if you go ahead and memorize them in this case. So that's the logarithm of a product is the sum of the logarithms property. And again, we have to each exponential property, we have a corresponding property of logarithms because of this kind of interplay between logarithms and exponential, two sides of the same coin. So the other exponential property we talked about was e to the x divided by e to the y. If you divide two exponentials, you subtract their exponents, is e to the x minus y. In the logarithm world, that comes out as follows. The logarithm of the quotient of a quotient is the difference of the logarithm. Okay, so and you can prove that in exactly the same way you did the product one. Then we had this friendly one. If you take an exponent of an exponential, so e to the x raised to the rth power is e to the x times r. So you multiply the exponents. In the logarithm world, if you take the logarithm of a to the r comes down in front of the logarithm, and you get r times ln a. And there's one more I'm probably missing. I mean, this is kind of a special case of the quotient one, but I guess it warrants its own thing. So, just negative exponents. E to the minus a is 1 over e to the a. So the ln of 1 over x is minus ln x. And this is a special case of this with the r is equal to 1. I mean, use above with r equals 1, but it comes up, oh, sorry, r equals minus 1. It comes up enough that it warrants its own privileged place in the column in the table, and I should use a just to be consistent here instead of x. But anyways, it's a special case of the previous property. Okay, so I said the reason I motivated these was that you can use these to solve logarithmic equations by combining the logs if necessary on one side of the equation. Before I do that, let's do some examples. So examples. Use properties of logs of logarithms to simplify the following expression. Five ln x minus 1/2 ln y plus 3 ln z. Okay, so when you're given, so what x, y, and z, we can think of them as just some old numbers, okay, good old numbers. When we're doing these kind of simplifications, I think the difficulty is in which property do you use first. And usually you have to use this property here, this exponent property first, to be able to then employ the other properties, right? Because you can't just go ahead and use the quotient property or the sum property right away, because you have numbers in front of this logarithms. You have 5.5 here and 3. So we first have to use the property, the third property in the table here. So we first need to use the property r ln x is, or r times ln a is ln a to the r. Okay, so if we do that, we get ln x to the 5th minus ln y to the 1/2. So this expression equals plus ln z cubed. And now you can use the quotient and sum property. You just have to do it in the right order. So I will bracket, you have to decide how to bracket the expression. I'll bracket it this way. So using the quotient property, this is ln x to the 5th over ln y to the 1/2 plus ln z cubed. So that's using ln a over b is ln a minus ln b. And then I can use the product property that ln a times b is ln a plus ln b. Use this in reverse, and you can write this as ln x to the 5th y to the 1/2 times z cubed. And so this becomes ln x to the 5th times z cubed over y to the 1/2. And if you want to be really fancy, you can write the y to the 1/2 as root y, but it's unnecessary. So ln x to the 5th z cubed over root y. And that's that's it. That's it, writing as a single logarithm. So that's kind of a fun problem. The other type of question that seems to like to come up on the homeworks is the following type of thing. So example 2. which of the following expressions is equal to, well, yeah, is equal to the expression ln 9x minus ln 3x, question mark. And so what it gives us is the following. It gives us 4 choices, so it's a multiple choice question. ln 6x, that's choice A. Choice B is ln 9x over ln 3x. Choice C is 6 times ln x. And choice D is ln 3. So I'm going to pause the video for a second and give yourself a moment to think about what the answer is here. Okay, so hopefully you've kind of had a chance to figure this out. So what I would do for a problem like this is, instead of kind of guess at it, I would just go ahead and simplify this guy here using properties of logs. That's what I would do. ln 9x minus ln 3x using properties of logs. Of ln's. So I'm going to use, the first thing I see when I look at this is I see a difference of ln's. Okay, so let's just mess around with that. So we have this, so this ln, this guy here, equals difference of ln's, the quotient, the logarithm of the quotient, so it's ln 9x over ln 3x. And now we can do some cancellation. That's ln of 9 over 3, so that's ln of 3, which we see is D. So the correct answer is D. Okay, so that's, again, there's like a bunch of problems like this on the homework. Just don't try to eyeball it. You can make an easy mistake. Just work it out using properties of logs on a separate scratch paper, and then just figure out what you get. If you don't get one of the answers, then you've made some kind of mistake, go back and fix it, right? Usual thing. The other type of thing that comes up on the homework is the following type of thing. So, so example 3. Using properties of logs, use properties of logs of ln's, logs, or a logarithm, natural logarithm, along with equation double star from the last video, which I'll state again. So this was e to the ln x equals x, to simplify expressions. So here's the example. So simplify the following expressions. E to the ln x plus ln 2, that's the first one. And the second one is e to the 6 times ln x squared. Okay. So for the first the first one, we use the property the ln of a times b is the ln, so this product property of the logarithm is the ln of a plus ln b with double star, with the equation double star, which I wrote above here, right? So this is this guy here. So this is fairly easy. So this is e to the ln of x plus ln2, that's the ln of 2x, right? And then the double star equation says that the e and the ln really cancel each other out, so this just equals 2x. And so that's number one. Oh, I already said that. Yeah, so that's number one. I should put the 1 here. So for the second one, for this one, we need to use the property, the exponent property of the logarithm. So this ln a to the r is r ln a. We need to use that property in reverse. So then 6 ln x squared, right, is equal to ln x squared to the 6th power, which is ln x to the 12. All right, and so e to the 6 times ln x squared, sorry, clean that up a bit, is e to the ln x to the 12, which by this handy dandy equation double star, which says if you take the exponential of a single logarithm, they cancel out, and so it's x to the 12. So that's what we get. So I did skip a step here, but I can write it in. So the step I skipped, I talked through, was just this one. Okay, so that's what I skipped there, but then I wrote out how to use the property here. So hopefully you're okay with that. Okay, so this is fairly straightforward. So finally, the whole point of this was to be able to solve logarithmic equations, right? That's how I motivated it at the end of the video, last video, so we can finally do that. So finally, we can solve a non-trivial logarithmic equation. So the equation I had chosen for you guys was the following one. So solve for x, ln x minus ln x squared plus ln x 6 equals 0. So the strategy for these kind of things is to basically, remember we had a strategy for exponential equations, and that was to isolate the exponential, then take the logarithm of both sides, and then solve an algebraic equation. So the strategy here is also in 3 parts, but instead of isolating the exponential, what you do with this kind of logarithmic equation is you use the properties of the logarithm of the ln to combine all the logarithms into a single logarithm on one side of the equation. So use the properties of the ln of the logarithm, of the natural logarithm, that we discussed above, to combine all the logarithms, or to write rather, to combine or write, to write one side of the equation as a single logarithm. And then 2, once you've done that, then exponentiate both sides of the equation. And use our wonderful equation double star which is this equation e to the ln x equals x, to obtain an algebraic equation for x. And then lastly, the third thing is solve the algebraic equation for x. Okay, so let's do it. So those are the 3 steps. So we have ln x minus ln x squared plus ln 6 equals 0. So I'm going to combine these two using the quotient property that ln a minus ln b is ln a over b. And then you get, so you get ln x over x squared plus ln 6 equals 0. So that's the equation you get. And actually notice here, I mean, we could keep combining at this point, but notice that you can actually do some very easy simplification. So that this is ln of 1 over x plus ln 6 equals 0. And then you get, now we can use this other property, this product property, that ln a plus ln of b is the ln of a times b. And so this is then ln 6 over x equals 0. And now you've done everything. You've written the right-hand side, so the left-hand side of this equation is a single logarithm. So now we can exponentiate both sides of the equation. Okay, so if you do that, you get e to the ln 6 over x equals e to the 0. And you have to remember that anything to the 0 is 1. Otherwise, this is not going to go well. And so then using our double star, this becomes 6 over the e and the ln cancel because you have a single logarithm here now. So this is double star. So you get 6 over x equals 1. And now finally we solve this algebraic equation for x. And when you do that, you just, you have x over 6 is 1. And so you get, you can cross multiply, whatever you want to do, you get x equals 6. And that's the answer. So that's it, we did it. Okay, so all this stuff up so far basically has been pre-calculus type stuff. But like I said, even if you've seen this before, hopefully you enjoy seeing it again. You get a different perspective, and it's like something that's probably good to see more than once. But let me, I'd like to get into some calculus before I conclude this video. Before I do that, let me just warn you of some false properties of logarithms that people tend to use. So don't use these false properties of logarithms. So the ln of a plus b, the ln of a plus b is not equal to the ln of a times the ln of b, right? What's true is the ln of a plus the ln of b is equal to the ln of the product. But there is no way to simplify the ln, the logarithm of a sum of two things. And again, that's why I emphasize, if you think about the exponential properties, if you go back and you think about the exponential properties, there's no way to simplify e to the x plus e to the y, right? So that's the issue. And also, people occasionally do stuff like this. It is not true that the ln of a divided by the ln of b is not equal to the ln of a minus the ln of b. So these are kind of, so what is true is the ln of the quotient is equal to the ln of the difference. But there is no property to simplify the quotient of two logarithms. The logarithm of the quotient, okay. The quotient of two logarithms, there is no property for this. And similarly, there is no property for this. Is not equal to ln a to the r. What is true is r ln a is ln a to the r. But there is no way of simplifying an exponential of a logarithm. The logarithm of the exponential, okay. But the other way, it does not work. Okay, so I mentioned this because I've been doing this long enough to see that people get confused with these things. And so I wanted to make sure this doesn't happen. So yeah, just these are kind of false properties. False properties. They're not true. All right, so let's get back to calculus. We can do some more calculus now, because we have the ability of solving exponential equations, which we did not have before. So briefly back to calculus of exponential functions. And basically the issue is that now we can solve some problems before that we couldn't last week, couldn't before, because we can solve exponential equations using logarithms. Okay, so the thing to remember is things to recall, right? And all these things, and why we love the natural exponential, is that the derivative of e to the x is e to the x. That's the thing, that's what's going to be used in all these calculations. Okay, so here we go. So here's the first example. I'll do two examples of these types of things, and then you can play with more in your homework. So find the coordinates of the relative extremum of the given function, and determine whether that extremum is a min or max. Okay, relative min or relative max, I should say, so local min or max. All right, the function that it wants us to handle is f at x equals e to the minus x plus 4 times x. Okay, so remember, so recall, this is from now a couple weeks ago, but we've been doing this a lot to find the relative extrema of a function f at x. We set f prime at x equal to 0 and solve. And then when we have those solutions, we can apply the second derivative test to the solutions. In the very rare event that the second derivative test fails, we can go back and do the first derivative test. Hopefully it doesn't happen. And then we can apply the second derivative test to these solutions. Okay, so we look at this function f at x equals e to the minus 4x, sorry, e to the minus x plus 4x, f prime at x is then equal to the derivative of this guy, and that is the derivative of e to the minus x plus the derivative of 4x. Okay, the derivative of 4x, we've done this many times, is just equal to 4. So this is the derivative of this guy plus 4. And now you have to remember, how do I differentiate an exponential composed with another function? So back last week, we talked about how you differentiate e to the gx, something like e to the g of x. Derivative, so this is the exponential as the outer function and the inner function g of x. So it's taking the exponential of g of x. So the derivative of the exponential is always itself evaluated at the inner times the derivative of the inner. So that's the chain rule. This is relatively easy because the inner function is just minus x, right? So the derivative of the inner in our case will simply be minus 1, but I'll write it out. So this is equal to e to the minus x times the derivative of minus x plus 4. And so this is minus e to the minus x plus 4. And so that's the f prime at x. So I'm making such a stink about this because, I mean, even when I was teaching Calc 2, I mean, people still miss up this minus. And it completely changes the answer. It gives you some nonsense if you don't have it. So that's the derivative. That we now need to set this equal to 0 and solve. So you get 0 is equal to e to the minus e to the x plus 4. And so you get 4 is equal to e to the minus x. And now you can take now we can solve this exponential equation. Now we know how to do this. So now take ln's of both sides. So you get ln of 4 is equal to the ln of e to the minus x. And again, remember now this rule from the last video that the ln of e to the r is r for all numbers r, right? What do you have to raise e to the minus x to get e to the minus x? Well, that's minus x. So we get x is equal to the minus of ln, negative ln 4. And if you like, you could use this other property of logs that I mentioned, that this is just ln of 1/4. But you know, it's a special case of the exponential property. Okay, so that's the potential extremum point. Now we need to check if this is a min or a max. Now we need to use a second derivative test. To check if this point is a min or max. So where is this first derivative? So I need to bring this back downstairs here. Okay, I'll erase the red box. Okay, so the second derivative is the derivative of this guy. And you go through the motions again, but this is minus the derivative of this. Of course, the derivative of 4 is 0, and this is minus e to the minus x, just as before. So in this case, it is just e to the minus x, the second derivative. And now it's good. Now we're going to plug in, and it's actually good we wrote this as, you can see it's good that we wrote this as x is ln 1/4. We're going to plug in ln 1/4 into this and use double star to rewrite this, to figure out what the sign, to evaluate the second derivative at this point. So f double prime at ln 1/4, actually doesn't matter, we could plug in the other thing, but is e to the minus ln 1/4 is, again, using this other property of the log, is right, this is e to the 1/4 to the minus 1 power. So it's e to the ln of 4, which by their double star is 4. So that's positive. Let's clean that up a bit. So actually, maybe it was easier to leave it as minus ln 4. I wouldn't have to do the extra step again, but it's fine. Right, so you need to write it as a single logarithm to be able to use this double star. Right? And here I use the exponent property again. I brought this exponent. Right? This is this property r ln a is ln a to the r with r equals -1. That's that special case of the property. So f double prime at ln of 1/4 is positive. The graph is bending up there, so we have a min. So x equals ln 1/4 is a min. And I think it wants us to find the y value also. I think the question wanted that. So the coordinates of the min of this local minimum are the ln of 1/4 and then f of 1/4. And so f of 1/4, you have to remember what f at x is. It's way up above. So I'll just say what it is here. F at x was this, e to the minus x plus 4x. So f of 1/4 of ln 1/4, oh, sorry, ln of 1/4. So f of the ln of 1/4 is e to the minus ln of 1/4 plus 4 times the logarithm of 1/4. And we just figured out, we just computed that this was equal to 4. So this is 4, and I don't know if you want to say it this way, it's minus plus minus the ln of 4 to the 4th power, or you can just do 4 minus ln 4. 4 ln 4 is probably fine. I might leave it like that. So 4 times 1 minus ln, the ln of 4. Okay, I mean, you could go on trying to simplify this, but there's really no point. Okay, so I hope that's okay. And that's, so the minimum, those are the coordinates of the minimum point. With the x value being the ln of a quarter, and then if you have value of the function there, that's what you get. Okay. So I'll do one more problem and then we'll call it for this video. So example 2. So part A, find the point on the graph of y equals e to the minus x, where the slope has tangent, where this tangent line has slope -8. And then part B, plot the graph of y equals e to the minus x, and along with the tangent. The tangent line, whose slope is -8. Okay, so there's actually kind of a lot in this question. And we have to remember, this is actually going back quite a ways. We haven't talked about tangent lines directly in quite some time, right? So let's focus on, so here's the answer. Let's focus on part A first. We'll worry about the graph in a second. And we haven't quite talked about graphs yet because it didn't come up last week. So this is a good point. So what are we being asked for here? We have to translate this question, like this words, into a mathematical equation we can solve, right? So we want to find the point in the graph where the tangent line has slope -8, right? What function gives us the slope of the tangent line? Right, this is going way, way back. So you need to recall that the slope of the tangent line at x is the value f prime at x, is the derivative. So it's like we're going way back to like a couple months ago, right? The derivative gives you the slope of the tangent line at the point x. The derivative function is the slope function. So what we're asked to do in the first part is what we're tasked to do is to find the x for which the derivative is equal to -8, right? So we want to find x such that the slope of the tangent line at x is equal to -8. So that's the equation we need to find and solve. So we need to find the derivative. So to solve this, to solve this problem, we need to find f prime at x and set it equal to -8 and solve for x. And if you think about it, what we've been doing when we've been finding these minima and maxima, the first step is to like find where the tangent lines are flat, right? Because if you have a min or a max, you've got a min and the tangent line is flat at the min. If you've got a max, the tangent line is flat at the max. So this, what we did, we set f prime x equal to 0, which means that tangent line is flat at that, has 0 slope or is flat at those points, and then we solved for the x. So this is a different take on that. You're setting it equal to -8 and so on. Okay, so now where did the f prime, where did the function go? It's really easy. So this is the same thing we were looking at before. I mean, the derivative, so f at x was equal to e to the minus x, and just like above, the derivative is just going to be by the chain rule minus e to the minus x. So this is the derivative of the inner, and this is the derivative of outer at inner. Right? Okay, so set f prime at x equal to -8, and you get -8 equals minus e to the minus x, and you get 8 is equal to e to the minus x. Cancel the negatives. Now you take ln of both sides. ln 8 is ln of e to the minus x. And so you get minus x is ln 8. And so x is minus ln 8. Okay, so it's going to be useful to have a bit of an approximation of this, so you can use your calculator. So if we kind of put this into a calculator, so this is approximately minus 0.2709, because in the end, what you're going to have to do is you're going to have to choose a graph off of the homework. And so it's good to kind of know roughly what it is, but I'll draw the graph for you anyway. So part B, the graph. So, and I should just use this to illustrate what the graph of e to the x looks like versus the graph of e to the minus x. So the graph of y equals e to the x has the following form. So e to the 0 is 1, so it has a y-intercept of 1. And it just grows, like this is exponential growth. We talked about this last week, right? E is approximately 2.718. So this is just going to grow very fast out to infinity. If you start putting in negative, like very large negative numbers, right? It's like if you had e to the minus 100, that's 1 over e to the 100. That's going to be very, very small. And if you did e to the minus 10,000, well, that's 1 over e to the 10,000. E to the 10,000 is huge, so this is extremely, he's very, very, very small. So as you go out to minus infinity, the graph is going to get closer and closer to the x-axis, but never quite reach it. You just get smaller and smaller numbers. So this is the graph of e to the x. The graph of minus e to the x is the reflection of this about the x-axis, y-axis. So this is the graph. The graph of y equals e to the minus x is the reflection of this graph. So this is supposed to be the same length. Didn't draw it great. Let me try it again. That ain't too bad. So this is supposed to be the same distance. So the graph of y equals e to the minus x is the graph of y equals e to the x reflected about the y-axis. So you probably learned that in Math 112 or some other class that the transformation that maps f of x to f of minus x just reflects the graph about the y-axis, and that's what this is doing. And so for us, right, we have the graph of e to the minus x, and we want to draw the tangent line at approximately -2. So our graph looks like the following. So this is 0.01. We're going to go just below -2, right? It's like -2.079. So just like somewhere over here. So here's -2, and then you go like just below it. And then draw the tangent line. And then the slope is -8. So on the homework, what you'll see is that there will be a bunch of graphs, and you'll have to pick which one is right. You don't have to draw the graph yourself, but you have to play this kind of a game. So you have to kind of figure out exactly where the value is, roughly where it is, and then pick the right graph. But I'll let you do that. So I've done enough of your homework already. But those are the two things I wanted to do. And this is a nice example because I didn't talk about the graphs of the exponentials last time. Because we actually didn't really come up on the homework at all last week, but it does come up here, and so it's a good thing to talk about. And if you want to know more in more detail why the graphs look the way they do, I can go into some more detail in the live meetings. But this is fine for now. So just remember roughly what they look like. All right, so that's it for now. So what remains to be done for this week, and then in the final video, which will be video 21, is the derivative of the logarithm and differentiating logarithm functions. And that's a little trickier than the exponential. The derivative of the logarithm tends to be more complicated. And so second derivative of logarithm functions can be very messy. I mean, hopefully we won't have to do much of that, but that's what's coming next. All right, thanks for tuning in.